All right, here we go back with the models of hydrogen. In this statement, we have, in Bohr's theory of hydrogen, the electron in its ground state was supposed to travel in a circle of radius 5 times 10 to the negative 11 meters. I believe that's the angstrom, or A naught in quantum theory. Held in orbit by the Coulomb attraction of a proton. According to classical electrical dynamics, this electron should radiate and hence spiral into the nucleus. Show that for V much less than C, for most of the trip, you can use the 𝘰𝘰𝘠𝘰𝘠 formula and calculate the lifespan of Bohr's atom. Assume each revolution is essentially circular. Okay, why circular? Well, then you get centripetal acceleration. All right, so, and much like in the previous question, find the acceleration from the force law. But before we can use this acceleration, we must check that the velocity is non-relativistic. Otherwise, we can't use the classical models. So for V much less than C, we have V over C is much less than 1. That is the needed condition. So for F equal ma, we have the attraction. So 1 over 4 pi epsilon naught little q squared over r squared is equal to V squared over r. So V here is equal to 1 over 4 pi epsilon naught q squared over mr. Thus, V over C, if we take the fraction and we take their fraction, we need to ensure that this is sufficiently small. So 1 over C times the velocity, which we just found is the square root. Chug that through, we see that we get 0.0075. Even when the radius is goes smaller, divided by 100, which is, multiply everything by a factor of 10 here, because we have 1 over 100 in the square root, so that gives us a factor of 10 outside. The radius is only 10 times greater, so 0.075. So for most of the trip, the velocity is safely non-relativistic. Again, we're assuming this because we're told that it should be radiating towards the nucleus. So if that's the case, the radius gets smaller. If the radius gets smaller, we normally speed up, but we don't speed up enough to consider relativistic mechanics. All right, so with this, we can use a 𝘰𝘰𝘠𝘰𝘠 formula safely. So P is equal to mu naught q squared a squared over 6 pi c. Plug in the a squared that we found. Okay. Here we just got to be careful because we know that a is equal to v squared over r from the centripetal. And if we set that equal to what we found in the force equation, then we see that we get a 1 over 4 pi epsilon naught q squared over mr squared all squared. So be very aware of that. Here, though, we see that power is equal to the negative du dt, where u is the total energy of the electron. Again, it's supposed to be radiated, so the negative tells us that we're losing it. With that being said, if u is equal to the total energy, then we have to have the kinetic and the potential. The kinetic is 1/2 mv squared. Potential is q squared over r, with the SI units for this particular interaction, 1 over 4 pi epsilon naught. So if we try to maneuver everything, if we put in if we force factor a v in there, or an r factor in there by multiplying by r over r, then we can substitute in the v squared r that we found from the force relation again. And that's why the kinetic term goes to 1/2 r dot 1 over 4 pi epsilon naught q squared over r. That should be a q squared over r, excuse me, not r squared. Okay. No, I lied. It should be, okay, fair enough, it should be r squared. But nonetheless, what we have to do now is factor out, because we multiply, okay, yeah. So I'm just overthinking it, sorry guys. So yeah, now we can simplify down, and we see that we get a negative 1 over 8 pi epsilon naught q squared over r. So if that's the case, take the time derivative by setting that up, using the power rule on r to the negative 1. We get negative signs canceling, and we're left with negative 2 in the r power. And then, of course, we have to take dr dt because we don't know what that is. So implicit differentiation, working with the chain rule here. Simplify down, you see that we get 1 over 8 pi epsilon naught q squared over r squared dr dt. Okay, fair enough. Now what we have to do is set this equal to the power we found from the 𝘰𝘰𝘠𝘰𝘠 formula and set the two quantities equal. Again, put the negative sign on the du dt term. So we see we get a bunch of cancellations, pi's cancel, q's cancel. We still have to find what dr dt is. And so what we do is sub everything over, push everything over that we can after the first wave of simplification. We still have that squared term for the power, so we have to, knock as much of that out as we can. I tried color coordinating everything to the best of my ability, but as you see, we have much more to deal with. Now that we multiplied over an epsilon naught, we can combine that with the mu naught to put a C term in there. And just, take your time simplifying. What we're left with out front is a negative 1 over 3c term, and then everything else is a square. So we have 2 pi epsilon naught mc squared times 1 over r squared. That was a simplifying fact. That was dRdt. And from this, we can find the time because we know what the radius should be. So here, if we push over the dt from the r and do separation of variables, just like solving a differential equation, knock all the constants over to the other side in the next step. You see that we can integrate both sides, and then we get a t, or really delta t, but we're assuming that 0 is the other term. So with this, we start at r naught, and then we go to 0 because we're supposed to radiate towards the nucleus, which would drive the radius to 0. Okay, so with this, we get a r cubed over 3, evaluate it from 0 to r naught. The 3's cancel. We like that. Clearly, 0 cubed is 0, and then minus the r naught, so we get the negative signs canceling. And we see that the time that this thing would live within this Bohr model would be c is equal to 2 pi c times the square of 2 pi epsilon naught mc over q squared times r naught cubed. Okay? And numerically, what we could see is once we plug in all the constants and square everything, or cube for the case of the radius, we get 1.3 times 10 to the negative 11 seconds. That's not very long.